solid conducting sphere. In a simple thing, I'll write it iron. This is center. No, I want the field strength at point P1. So for that, what I'll do is I'll assume a Gaussian surface. And now when you give a charge to this iron sphere, where do it will reside? What is this dotted one? It's a Gaussian surface here. Why I assume a Gaussian surface like this? Why not any other shape? Again, once again, the very fundamental thing is what? Like what all we give charge will reside only on the surface of conductor. What all we give charge will reside only on the surface of a conductor. Then, what is the electric field strength at point P1? I want to calculate. Shall we use Gauss law? So here I'll assume a Gaussian surface, ds. Everywhere E bar will be perpendicular to this. So integral of E bar dot ds bar equal to q in by epsilon naught. What is dotted? Here after this is a Gaussian surface. Okay, no. This will be E bar dot ds q in by epsilon naught. No. What is the net charge enclosed by the Gaussian surface? Q only. But sir, like a charge is not present at the center. It's not a point charge. Already we have made no. In a Gaussian surface, what will be the charge? If whether Gaussian surface enclose a point charge or a charge body, what will be that one? What is the net charge enclosed? It's Q only. So this will become integral of EDS cos 0 degree Q by epsilon naught. Okay, further, what is the angle between E bar ds? E1, it is. Angle between them 0 degrees. So therefore, this will become E1 integral of ds. So Q by epsilon naught. Now, what is the integral of ds? Football patches, like that football patches, if you add what you get surface area of a football. So E1 4 pi r square Q by epsilon naught. So what is the electric field at point 1? Q by 4 pi epsilon naught r square, or in a simplified way, KQ by r square. And now it will be radially outward. So how the lines of force we have to show it? Small diagram. How the lines of force should be radially outward. Okay, this one. So this is the radius of the sphere. So the field strength what we have calculated is point P1 here. How much it is? E1 equal to how much at point P1. So where do the field will be there? Now on the surface, let me pick up a point. On the surface, how much it should be? EP2, I'll write it. So here, EP1 equal to E1, EP2. So KQ by R squared. So what is the field on the surface of conductor? Let me rewrite this. Okay, there's a first formula. Field on the point, external to point, no, outside the sphere. Next, we have field inside. Field on the surface. On the surface, how much it is? KQ by R square, because what is the point? Point lies on the surface. Now, what about field inside? So what is inside? Inside, the point will be somewhere here. What about field inside? Due to static charges, it should be zero, no? Now, why it should be zero? On the surface of conducting, or on the surface of charged sphere. Field inside the charged sphere, because I'll use word that charged. Why, sir, you made zero? Why not let it be non-zero? Anything will happen if it becomes non-zero. Again, law of condition fringe will get violated. So if you give a charge to a conductor, where do it will reside? It will reside only on the surface. So shall we define surface charge density? So how you define surface charge density? Q by 4 pi R squared. Okay, after getting this E bar, can we calculate potential? Now you can ask one very beautiful question. I think I was just waiting. Sir, why you are writing Q? Can I replace this with a point charge? Then also we'll get same answer, no? KQ by R square. Sir, is it a where charge is present? Say for at point P1, some charge is present very near and this charge is present some far away. Is it all the charge? Will it be at same distance from point P1? No. We'll look at this one. Then, but sir, the way you are writing as if this will be like a point charge, as it is. If the charge is distributed symmetrically with respect to center of Gaussian surface, then the charge of a body can be replaced with a point charge kept at the center of Gaussian surface. I'll repeat once again. If the charge of a body is distributed symmetrically with respect to center of Gaussian surface, then the whole charge of a body can be treated like a point charge kept at the center of Gaussian surface. Okay, now what is the field if I keep a point charge here at a distance, or what is the field? KQ by R squared. It is similar to this. So if you stand at Gaussian surface, though it's a charged sphere where charge is present only on surface, it will be equivalent to point charge kept at the center of Gaussian surface. That's what this equation is concluding. So now we know potential. So what can be potential? Directly shall we write here only? What should be the electric potential? Electric potential at point P1. KQ by R square. Then what is the potential on the surface? Sorry, KQ by small r, KQ by capital R. We have the total description here. So what is the field strength outside? KQ by R square. So similarly, what is the potential outside the charge conducting sphere given by this formula? What is the potential on the surface? KQ by R. Now, what about potential inside? Will be that of the on the surface. Any reason for that? Because what is the net field inside the conductor? Should be zero. Conductor should be equipotential. So what is the potential on the surface? That will be the potential everywhere, because the net field inside the conductor should be zero due to static charges. So therefore, we know conductor is what? What is the reason for that? Again, why we should write Vp3 equal to Vs? Because conductor is an equipotential surface. So because of that, the net field inside the conductor must be zero. and conductor more is equipotential surface. So potential difference between any 2 points inside the conductor must be 0. I'll take potential difference between point P2 and P3. It should be 0 because they're on like in a conductor. So what is the potential at point P2? That on the surface. So therefore, potential anywhere inside also should be same. These are very, very fundamental thing. Potential inside. Or you draw a Gaussian, later on I'll come. If you draw a Gaussian surface here, what is the net charge enclosed will be 0. Because of that, the field will be 0. We can define that also. Let me begin like this. No Gaussian surface. Sir, you draw a Gaussian surface here. If I draw a Gaussian surface here, okay, let's give explanation in other way also. Now, why electric field inside the conductor must be 0? So the Gauss law will give still more a better example for us. So here I'll assume a Gaussian surface. Where it is Gaussian surface, now it is inside the material of the sphere. What is this? It's a Gaussian surface. Where the charge given will reside only on the surface. So and the point P2 is here, or point P3, no, what we took it. Yeah, there's a thing. Okay, now what is the net charge and what is this dotted circle? Gaussian surface. And this is a conducting sphere. Charged conducting sphere. Where the charge will decide. So what is the field strength at point P3? So what is the net charge enclosed by Gaussian surface? 0, no. So therefore the field is 0. But sir, like this will not produce field. I am not saying it will not produce field. Produce field. So what field produced by this, like a sector, equal and opposite will be produced by this. So net field at point P3 will be 0. Don't say that this will not produce any field here. This will produce field. This region also will produce field. The vector sum of all the field at this point due to all the charged regions will be 0. Therefore, the field is net field is 0. I think what Gauss law says, instead of all that mathematics, what is the net charge enclosed by Gaussian surface? 0. So therefore, field is 0. So if you, what is the other explanation? What you have to give? The field produced by this region will be towards left, and the field produced by this region will be towards right. So equal and opposite, the net field will be 0. Net charge enclosed by Gaussian surface is 0. Therefore, Qin is 0. So then what will be this expression? EP3 dot ds equals 0. ds should be non-zero. then what should be 0? EP3 0. I think this is a mathematical way the Gauss is trying to explain. So what should be the net electric field inside the conductor due to static charges? Must be 0. Conductor must be equipotential. What is the potential on the surface of conductor? That should be the potential everywhere inside. So when you go for the variation of this field graphically, so I think we can show it, the electric field as well as also the potential. So the electric field will be this is center, this is capital R. So this field will be how much? Similarly, what about the potential? Potential it will be a straight line. Potential that is there on the center will be everywhere inside the conductor. No, outside what happen? It will become, it start decreasing. Okay, there's a variation of the electric field and potential due to a charged conducting sphere. Any doubt you can clarify it? I will continue because this will not help you to solve any of the problems. We have plenty of still ideas to be discussed. Okay, let me continue for another 1 hour so that the whole set will get, because again, the half of the concept is what I covered it. Remaining of still are there. Let me continue for another 1 hour. Or shall I give any break? Some 10 minutes break if you want, then afterwards I'll continue. It's left to you. Can I continue?
Sir, 10 minutes break.
10 minutes break. Okay, we'll do one thing. 10, 10.